Someday the universe will end, and its last moments could look surprisingly ordinary, a slow fade, a violent tear, or a gentle collapse. One possibility is everything cooling down until nothing moves. Think of a hot mug of coffee left on the table until it's room temperature and boring. On cosmic scales that's called heat death. Another is space stretching so wildly that galaxies, stars, even atoms are pulled apart. Picture a rubber band stretched until it snaps, but on a scale you can't fit in your pocket. A third is everything falling back together, like squeezing a balloon until it pops inward, a cosmic rewind. Stick around and first we'll paint each ending in plain language, with everyday examples and a few surprising facts that make these huge ideas feel strangely familiar. You'll walk away with clear mental pictures, great for impressing friends, a sense of why scientists care, and maybe a tiny laugh about the universe's slow, dramatic or oddly quiet last act. A dramatic clock, measuring cosmic time. Light from faraway objects reaches us after taking a long trip across space, so when astronomers look out they are literally looking back in time. That light is stretched as the universe expands, which makes colors shift toward the red end of the spectrum, a simple effect called redshift, like hearing a siren drop in pitch as it speeds away. You can think of it the way a stretched rubber band changes a note on a plucked string. Stretch the space and the light's note shifts. Lightning and thunder give a handy daily example. You see the flash first and hear the boom later, because light and sound take different times to travel. The sky's light gives astronomers a record of past events in the same way. Galaxies moving away from us act like ticks on a cosmic clock, with farther ones showing more stretching. This is similar to raisins in a rising loaf of bread. The dough expands and every raisin moves farther from its neighbors, without any raisin being singled out as the center. Simple observations of how light is stretched and how bright objects appear tell scientists how fast the universe has been stretching, and how that stretching has changed over time. It's like watching the speedometer of a car from a distance by the blur of scenery. You can tell whether the ride is steady, slowing, or picking up speed without ever being in the vehicle. Other clocks complement the sky's light. Radioactive elements inside rocks act like tiny hourglasses. Unstable atoms slowly turn into stable ones at a steady pace, and by comparing the amounts of parent and daughter atoms scientists can infer how long that process has been running. That method is used on meteorites and planetary materials and works a bit like counting the wear on a shoe to estimate how many miles it has walked. Pulsars, dense, spinning stellar leftovers that flash with regular beats, behave like precision watches in the cosmos. Their pulses can be so steady that astronomers use them to time events and to search for subtle ripples in spacetime. Think of them as cosmic metronomes that refuse to skip a beat. White dwarfs cooling down provide yet another slow clock. Their fading glow tells a tale of long-term cooling the way a hot cup of coffee gradually loses heat on a table. Because no single clock is perfect, scientists cross-check many methods for a reliable timeline. Light travel records, decay rates in rocks, pulsar beats, and stellar cooling all point to the same broad story, and when one method disagrees it sends researchers back to the lab or the telescope for a closer look. Even everyday technology illustrates the care needed. Global navigation satellites must account for tiny effects of motion and gravity on time, or your phone would happily steer you into a lake. In cosmic terms, that means measuring time is not just looking at a watch, it's correcting the watch for the road it's traveled. Recent observations add a wrinkle. The rate at which the cosmic clock ticks can change, because the expansion itself is responding to forces we do not fully understand. Astronomers track both the stretching of light and the apparent brightness of distant objects to see whether the expansion is steady or speeding up. Picture pressing harder on a car's gas pedal as you climb a hill. The countdown to some far-off destination depends on how the pedal is pushed. The whole enterprise has a bit of scientific detective work and a dash of humor. The universe keeps its own schedule, and we are charmingly terrible at reading it without several different kinds of clocks and a lot of coffee. Heat death and the ultimate nap. At the very end, the cosmos could settle into a state where energy is smeared out so evenly that nothing can do useful work anymore. That spreading out is what scientists talk about when they mention entropy, a word for how ordered things become more mixed up over time. think of a tidy bedroom left alone until toys and clothes are everywhere, or a drop of ink that disperses through a glass of water until the whole thing is the same color. When energy is evenly spread, heat stops flowing from hot to cold, engines stop running, and chemical reactions that power life simply can't be driven. Stars and other bright objects are the universe's workhorses, burning fuel and creating the differences in energy that let things happen. Over extremely long stretches they exhaust their easy fuel sources and cool, leaving behind dark, inert remnants. Some massive objects called black holes would hang around as the last concentrated bits, but even they are expected, by well-established theory, to leak energy very slowly and fade away like a candle that burns so faintly you need a microscope to notice the wick. Certain particle processes that scientists have proposed could further erode matter, though some of those ideas remain unproven. The core point is that whatever clumps or structures remain eventually give up their ability to drive change. Visual cues from everyday life make the idea less abstract. A hot cup of coffee on a cold morning cools until your mug and the room are the same temperature, and you can't get useful heat from it anymore. That's exactly the kind of thing happening on cosmic scale. A drained battery in a TV remote is another useful image. Once the chemical potential is used up, the remote won't make the television obey, and no clever rearrangement of the battery will restore the lost energy. In a universe headed toward the final, sleepy phase, everything behaves like that coffee cup and that dead battery, warm and even, with no potential left to do work. The practical consequence for us is mostly philosophical and poetic. This ultimate quiet doesn't influence daily life or near-future technology. It is a way of understanding the long-term destiny of systems governed by the rules of thermodynamics and gravity. It can be framed with a bit of humor, the cosmos tucking itself in for an absurdly long nap, pulling a blanket of low-energy photons over every galaxy. But the underlying message is sober and simple, a future where change slows to a near stop because the universe has used up the differences that make change possible, and all that remains is a vast, uniform calm. Big Rip, when space tears apart. Some scientists propose that the push making the universe expand could grow stronger over time and eventually overcome every force that holds things together. Space itself would stretch faster and faster, and not because galaxies are charging through a room, but because the room, space, is getting bigger. Think of drawing dots on a balloon and blowing it up. The dots drift apart as the rubber expands, except here the blowing is relentless and keeps speeding up. At first the biggest, most loosely held things would come apart. Galaxy clusters would loosen and float away from one another like neighbors drifting during a long, awkward party. Then galaxies would be unable to hold their stars in, and star systems would unwind. Short sentence. Planetary orbits would fail next, leaving planets wandering and lonely. After that, gravity and electromagnetic bonds that keep planets and people intact would be outmatched, and molecules and atoms would be pulled apart too. It's like pulling on a knitted sweater, you tug hard and the whole pattern starts to unravel, stitch by stitch. Putting it in everyday terms helps. Imagine stretching taffy slowly, it stretches, stays connected, and behaves predictably. Now imagine the pull keeps getting stronger and stronger until the taffy snaps into bits. Or picture Velcro being yanked faster and faster, first the big pieces come free, then the tiny hooks give way. That's analogous to how different scales of structure in the universe would fail under relentless expansion. Even something as small as the bonds holding electrons to nuclei would be at risk in the most extreme version of this idea. This scenario is a possibility, not a certainty, and it depends on whether the push behind expansion grows with time. Current observations allow many interpretations, and the version that rips everything apart requires that the repulsive effect become ever more dominant. So there's no need to panic about your coffee mug or your socks right now. Still, entertaining the idea sharpens our thinking about how cosmic forces work, and it makes for a dramatic story, a universe that ends not with a bang but with a gradual, unstoppable tearing, strangely poetic and a little unnerving. Vacuum decay, a phantom threat. Our universe might be sitting in a kind of energy puddle that is not the deepest possible puddle, and that simple fact drives the whole idea. Scientists use a phrase for this situation, but in plain terms it means the state of the vacuum, the background that sets how particles and forces behave, could be only temporarily comfortable rather than truly stable. If a tiny region were to slip into a lower energy state, that region would grow outward like a bubble and carry different rules of physics with it. The change would not be a gentle rearrangement, it would rewrite the connections that hold atoms together. A helpful everyday picture is a marble in a shallow bowl that sits comfortably but could roll into a deeper valley if pushed over the rim. Sometimes a nudge is needed, sometimes quantum effects provide a tiny, random hop that gets the marble across. Another useful example is supercooled water. It can stay liquid below freezing, but if disturbed a sudden crystal grows and the whole cup snaps to ice. In the vacuum case, the disturbance is a quantum fluke that creates a seed of the lower energy state. That seed behaves like a soap bubble and expands at near the speed of light, leaving behind a region where the basic constants and particle masses might be different. One moment your coffee is held together by chemistry, the next, the connectors that make atoms stick could vanish. The practical effects inside that expanding bubble are hard to overstate. Chemical bonds would fail, nuclei could break apart or form different structures, and the forces that give particles their properties could change. Think of it as having the plastic connectors in all your Lego sets suddenly change shape, nothing fits anymore and the whole model collapses. There would be no gradual warning. Because the front moves so fast, causality prevents information from outrunning it, you would learn of the change only when it is already upon you. That lack of warning makes the scenario eerie, but it is also why the phenomenon is discussed more as a theoretical boundary case than an immediate danger. Current evidence leans toward either a stable vacuum or one so long-lived that it is effectively permanent for any practical concern. Measurements of the Higgs field and related particles give researchers constraints on whether the vacuum is truly stable or only metastable, but the picture is subtle and depends on precise values that experiments are still pinning down. High-energy machines on Earth cannot realistically create conditions more extreme than what nature already produces with cosmic rays, and those natural high-energy events have not triggered anything catastrophic. So there is no reason to cancel everyday plans or build a bunker. The possibility remains a fascinating, slightly spooky thought experiment that helps physicists probe the limits of our theories, and it supplies just enough drama to spice up a coffee break without wrecking it. Proton decay and the slow unraveling. Protons, the positively charged cores inside every atom, are treated as essentially permanent by the simple rules that govern most everyday physics, yet some deeper ideas in particle physics allow for the possibility that they might very slowly fall apart. That notion, called proton decay, means a proton could change into lighter particles, such as tiny bits of energy and other small particles that no longer form the stable nucleus we recognize. In plain terms, something that seems permanent in a chair, a stone, or your own body might, under this hypothesis, eventually stop being made of the protons that once held it together. The change would not be dramatic like a chair exploding, instead it would be a vanishing act played out one proton at a time. If protons do decay, the effect on ordinary matter is subtle at first and utterly bewildering on the longest scales. Everyday chemistry would be unchanged for any reasonable human timescale, because proton decay, if it happens at all, is an extremely rare event for any single proton. Over unimaginably long stretches, though, entire atoms would lose their cores and disintegrate into lighter particles and radiation. A life example helps. Think of a brick wall in a seaside town battered not by waves but by single spray droplets that take eons to wear it down, each droplet small but steady. The wall does not crumble overnight. Similarly, matter would fade away grain by grain, atom by atom, until there is almost nothing left that resembles the structured stuff we know. Scientists test this idea with enormous, quiet experiments placed deep underground where the noise of ordinary life, cosmic rays and surface radiation, doesn't drown out faint signals. Gigantic tanks filled with clear water or other materials are watched by sensitive light detectors, waiting for a tiny flash that would betray a proton breaking up. No such flashes have been seen so far. That absence tells researchers that if proton decay happens, it is rarer than the limits these detectors can currently probe, meaning a single proton would typically last far longer than the entire span of time humans have been around, and in fact much longer than the familiar lifetime of stars and galaxies. The long-term consequence for the cosmos, should proton decay be real, is a slow unraveling of the material universe into a thin soup of low-mass particles and radiation. Complex chemistry would eventually end because atoms would no longer hold their nuclei, planets and solids would steadily lose mass and structure, even information encoded in matter would be hard to keep. It's a bit like leaving a box of crackers in a humid basement and watching them lose crispness drop by drop, only the basement is the universe and the timescale is beyond imagination. A touch of cosmic humor: while humanity frets about short-term waste and clutter, the universe might be practicing extreme minimalism, clearing out matter one reluctant proton at a time. Black hole evaporation, the last light. Black holes are not perfectly silent garbage bins. They can slowly leak energy in the form of particles and faint light, a process predicted by physicists. This leakage happens near the point of no return around a black hole, the boundary beyond which nothing can escape. Think of that boundary as a very steep hill. Get past the top and you can't climb back. In simple terms, empty space near that boundary can spontaneously produce pairs of particles, and if one of the pair falls in while the other escapes, the black hole effectively loses a tiny bit of mass. That escaped partner is what we call the last light from the black hole, in a way that sounds almost poetic but is really physics. Smaller black holes shine more brightly, in a relative sense, because they are hotter and lose mass faster than larger ones. Picture two candles, one big and one tiny. The small one burns through its wax quicker and ends with a shorter, sometimes sharper, flicker. The physics here means that as a black hole shrinks, its temperature goes up, so it radiates faster and shrinks even more. This runaway produces a dramatic finale. Near the very end, the emissions should shift to very high-energy forms of light, called gamma rays, which are much more energetic than visible light and behave more like stinging bee stings of radiation. Detecting that final flash would be hard, and funny enough, it's partly a problem of scale and timing. Most known black holes are huge and take far longer to evaporate than the age of the universe, so we won't see them wink out anytime soon. However, tiny hypothetical black holes would finish relatively quickly and could produce a rapid, intense burst of energetic particles. This is similar to watching a campfire. After hours of slow glowing embers there can be a sudden flare if a pocket of air reaches a hot spot. The physics burst is different, but the sudden brightness at the end gives a useful image. Practical searches for these final flashes use telescopes and detectors sensitive to high-energy radiation, the cosmic equivalent of fishermen waiting with specialized nets for rare fish. Astronomers compare signals from many directions and try to rule out more mundane sources like exploding stars or energetic storms in the galaxy. The job is tricky because the expected signals are brief and at very high energies, so instruments need to be both fast and sensitive, sort of like needing a camera that can snap a clear photo of a lightning bolt with no blur. Explaining the mechanism simply, quantum effects that normally live at the tiniest scales create particle-antiparticle pairs in empty space. The black hole's gravity can catch one while letting the other go. You can liken that to being in a crowded subway where one passenger gets pulled onto a train and their friend is left standing on the platform. The left-behind friend is the escaping particle, carrying away a sliver of the black hole's mass as if it were paid as rent. That bit of humor reflects an odd truth: even the darkest objects in the universe pay a tiny rent in light before they vanish. Finally, the last seconds would be extreme by everyday standards but are governed by simple trends. Less mass means hotter temperatures, which means faster loss of mass, which culminates in a brief, energetic burst. Observers would see a spike in very high-energy photons and particles, a cosmic mic drop if the event were close and the instruments ready. It would be both spectacular and brief, a final bright note in a long, quiet life, like the last firework at the end of a show that everyone remembers because it was loud and impossible to miss. The loneliest particles, neutrinos and photons passed. Neutrinos and photons are the particles most likely to survive when everything else has thinned away, and that simple fact makes them unique messengers from the last moments of a dying cosmos. Photons are simply packets of light, everything from the light that lets you read a book to the radio waves that bring music to your phone. Neutrinos are tiny, nearly invisible particles that barely notice anything around them. They slip through planets like a ghost walking through walls. Everyday life offers easy comparisons. A sunbeam that warms your face is made of photons, while the neutrinos from the same star sail through your body without so much as a hello. Photons can be bounced, absorbed, and scattered by matter, which changes their direction and color. That scattering is why the sky turns red at sunset. Shorter blue light gets scattered out, leaving redder light to reach your eyes. Stretching of space or passing near a heavy mass can drain photons of energy too, making them shift to longer, colder wavelengths, a bit like pulling a rubber band until the sound it makes becomes lower. Neutrinos, by contrast, rarely interact. They carry information from deep inside extreme places because they don't get stuck on the way out. They act like an honest courier that refuses to gossip with anything it passes. Because photons and neutrinos escape so well, they are the main sources of real information about extreme final stages, what was dense, what was hot, and how violent the last moments were. Instruments on Earth catch photons in all bands, visible, radio, 10th ray, so we can see different faces of the same event. For neutrinos, scientists build enormous, quiet detectors filled with water or ice. When the rare neutrino finally interacts, it produces a tiny flash of light, like a single firefly blinking in a dark stadium. Neutrinos also have the quirky habit of changing their identity as they travel, switching flavors in a way that physicists compare to a dancer swapping shoes mid-performance. This is a real, observed behavior, and it matters because it affects what detectors will see. If the universe grows emptier and colder, photons become stretched longer and less energetic, eventually blending into a faint background that is hard to detect, while neutrinos continue their long, almost uninteracted journey. Radio waves, visible light, and high-energy gamma rays are all the same kind of particle, photons, just at different energies, and they all suffer dilution and energy loss over cosmic distances. Neutrinos, being so shy, would still crisscross that emptiness with little change, carrying a direct, if whisper quiet, record of the last inner conditions. In the end, photons may be the ones that warmed and colored a civilization's skies, but neutrinos are the stubborn introverts that keep the purest memory of what really happened. Quantum fluctuations in an empty universe. Even in what looks like perfect nothingness, tiny blips of energy keep happening all the time. The basic rule behind this is that you cannot pin down energy and time with absolute precision at the same instant, so the vacuum behaves like a restless sea rather than a featureless void. Think of it as a perfectly calm pond that still has microscopic ripples from an invisible breeze. The surface seems still until you zoom in close enough. Pairs of short-lived particles can appear out of this restlessness and then disappear, doing their brief dance before vanishing again. These so-called virtual particles are not party guests you can photograph, but their presence leaves fingerprints. In the lab, for instance, two very flat metal plates placed extremely close together feel a tiny push toward one another because the allowed fluctuations between the plates are different from those outside, a real effect called the Casimir force. You can also detect shifts in atomic energy levels that are best explained by the same vacuum jitter. So although the vacuum's antics are subtle, they are measurable, like a whisper that nudges a wind chime. When the cosmos becomes emptier and colder, those tiny blips remain the last ongoing activity. Without ordinary matter and heat, quantum fluctuations are the only show left on stage, occasionally producing a particle that survives a little longer than usual. On top of that, there is a dramatic possibility in some theories. The vacuum we live in might be metastable, like a ball sitting in a shallow dip on a hill. A sufficiently large fluctuation could push a small region over the hill into a lower energy state, creating a bubble of different vacuum that would expand outward at near light speed. If that happened, the bubble would rewrite the rules of physics inside it and sweep through space, an abrupt cosmic change triggered by what began as a tiny, probabilistic tremor. It's a sobering thought, and a little like a pothole suddenly appearing on a smooth road, annoying for drivers, existential for universes. People often ask whether these vacuum blips could be useful or dangerous. In everyday terms, they are neither useful nor a threat to us now, because their effects are vanishingly small in ordinary conditions and become relevant only when the universe is extremely empty or in the vicinity of extreme objects like black holes. Near a black hole's edge, for example, the separation of ephemeral particle pairs can allow one to escape and appear as real radiation, a process often used to explain how black holes can slowly lose mass. That shows how vacuum fluctuations, while subtle, can have real consequences under the right circumstances. Meanwhile, theory struggles with how to add up all the vacuum's contributions to the energy of empty space. Naive calculations give numbers wildly out of line with observations, so physicists know something important is missing in the picture. It's like estimating how many socks are in a dryer by guessing at the size of the machine and being off by many, many sock-filled laundromats. A playful way to think about the whole thing is that the universe, even in its final quiet hours, has a habit of hiccuping. Those hiccups are unpredictable, typically harmless, and occasionally portentous in theoretical scenarios. Scientists keep studying small laboratory effects and using careful math to understand these fluctuations better, because tiny blips in an otherwise empty cosmos may hold the key to deep puzzles about the nature of space, energy, and the ultimate fate of everything. Entropy marches on, the arrow of time. Hot tea left on a table will cool until it matches the room temperature, and that simple fact is a window into a deep principle: energy spreads out from concentrated places into more spread out ones. This spreading is what people call entropy in plain language, a count of how many ways the parts of a system can be arranged so that it looks the same overall. A hot mug has a lot of energy concentrated in a small region. Once the warmth seeps into the air, there are far more ways for that warmth to be arranged, and the system has moved to a more likely state. The same basic idea explains why perfume drifts across a room instead of jumping back into the bottle. A useful way to see why time seems to flow in one direction is to watch a video of a glass falling and shattering. Played forward it makes sense, played backward it looks absurd. The laws that govern individual particles at tiny scales are almost neutral about time, but when huge numbers of particles act together, the chances overwhelmingly favor outcomes where energy and order smear out. A neatly ordered deck of cards can be shuffled into many messy arrangements with one riffle, but getting back to the original order without deliberate effort is extremely unlikely. Everyday life offers the same lesson: laundry goes from folded to wrinkled much faster than it returns to folded without intervention. This irreversibility has real, practical consequences. Heat engines, like car motors and power plants, operate because hot and cold regions exist. They convert part of that energy into useful work but cannot be 100% efficient because some energy must be dispersed as waste heat. Refrigerators and air conditioners move heat from cool spaces to warm ones by using electrical energy. They buy order locally while increasing disorder overall. Batteries gradually lose usable capacity as internal chemical states drift toward more disordered configurations, which is why a phone left with a full screen and no charger will eventually power down and sulk. Living things are clever local exceptions. A plant builds neatly ordered structures like leaves and stems by harvesting sunlight, nutrients, and water, and in doing so it increases entropy in its surroundings by dumping heat and waste. Maintenance and effort are basically ways of pushing things back toward lower entropy locally. You fold the clothes, sweep the floor, replace a worn-out part, but the price is always paid elsewhere in the form of energy spent and disorder increased. Humor aside, that's why paying the electrician or changing the oil actually matters. Entropy is expensive in time and resources. On the grandest scale, the same tendency points toward an eventual state where gradients disappear and no useful work can be extracted from the environment. That idea helps explain why engineers, ecologists, and even economists care about energy flows and resource management. Systems that ignore how energy spreads tend to run into limits. Still, the arrow of time gives everyday life its shape, memories, cause and effect, project deadlines, and the comforting predictability that your coffee will cool unless you act. And if entropy can be thought of as the cosmos' way of insisting things get mixed up, then at least it provides a steady supply of excuses for forgetting where you put your keys. The end of stars, a silent night sky. Stars keep shining because they steadily convert simple gas into energy at their cores, sending light outward like an enormous, controlled campfire. This process is not instant, it takes place over a very long time, and different stars behave differently as their fuel runs low. Some sputter gently, others explode. Think of a small wood stove that can be tended for ages versus a fireworks rocket that burns bright and then is gone. The night sky hosts both kinds of performers. Smaller, common stars cool down slowly and end up as dense, hot embers called white dwarfs. Think of a coal that still glows after the flames die. They are compact, roughly the size of a planet but much heavier, and over unimaginable stretches they dim until they no longer give off visible light. Larger stars, on the other hand, can die in dramatic bursts that scatter material outward and leave behind exotic leftovers like ultradense neutron stars or invisible black holes. Those explosions are loud in energy terms but silent in space. There is no sound, only the sudden change in the light show. As more stars exhaust their fuel and settle into cold, dark leftovers, the familiar speckled ceiling of the night will thin. The brilliant pinpoints that people used for storytelling, navigation, and late-night pondering will steadily wink out. Picture a vast outdoor stadium where one by one the floodlights go off until only a faint, distant glow remains. It's quiet and stark. For anyone using the stars to steer a ship or calibrate a telescope, losing those reference points would be like trying to drive by memory on a foggy night, doable with other tools, but much harder and less romantic. Beyond practical loss, there is a mood to consider. A sky without twinkling stars would feel emptier, more solitary, like a theater after closing time when only the exit signs still glow. Telescopes would have to rely on faint, diffuse light or on clever tricks to find anything. Human culture would adapt, as it always does, switching light sources and metaphors. A little cosmic humor helps. You could say the universe has finally stopped binge-watching itself and hit the snooze button. Still, the reality is quieter and cooler, not sinister, just very, very calm, a final exhale of a once brilliant light show. Galactic archaeology, fossils of structure. Stars and gas in a galaxy don't form in a single event, they carry records of past collisions, bursts of star formation, and slow sedimentation of heavy elements. Astronomers read those records by looking at where stars are, how they move, and what they're made of. For example, long thin streams of stars that arc across the sky are often the shredded remains of smaller galaxies that wandered too close and were torn apart by gravity. The Sagittarius stream is one well-known case in our own galaxy, showing how a once coherent dwarf galaxy has been spread out like jam on toast. Chemical fingerprints are another powerful clue. Astronomers call elements heavier than helium metals, and the amount and mix of these metals in a star tell a story about its ancestors. Stars born long ago tend to have fewer heavy elements because there had been fewer generations of exploding stars to seed the gas. By contrast, younger stars usually show richer mixes of heavy elements. It's like comparing an old recipe with a modern fusion dish. You can tell how many cooks have been in the kitchen. This method, often called chemical tagging, allows researchers to link stars that form together even if they're now separated across the sky. Kinematics, the motions of stars, add a second layer of evidence. Some stars orbit in well-ordered disks, moving in the same direction as their neighbors, while others move on random, halo-like paths. Streams of stars typically share very similar motions because they originated from the same disrupted object. Modern surveys map positions and speeds for huge numbers of stars, and when a group of stars lines up in both space and motion, it's a strong sign of a fossil structure. Think of it as finding a set of luggage with the same unusual stickers at an airport. They probably belong to the same traveler. Dense clusters of stars, known as globular clusters, act like time capsules too. They are compact, gravitationally bound collections that formed early and often survive long after the galaxies around them change. Some of these clusters seem to have been born inside other galaxies and later captured, so their presence can mark past mergers. Observers also spot shell-like ripples and faint tidal tails around large galaxies. Those subtle features are the cosmic equivalent of tree rings or layers in a cliff face, revealing episodes of growth and upheaval. They are faint and require careful observation, but they are unmistakable once found. Putting all these lines of evidence together, structure, chemistry, and motion, allows astronomers to reconstruct a galaxy's past the way an archaeologist pieces together a ruined city. The work can be painstaking and surprising. Sometimes a small, previously unnoticed feature explains a big part of a galaxy's history, like finding an old family photograph in a box of junk and realizing it changes the family story. And yes, the universe has a sense of humor. The relics are often spectacularly messy, like a backyard after a party where every guest left a piece of furniture behind. The cosmic microwave background fading away. The leftover glow from the universe's beginning now fills space with a faint microwave warmth sitting at about 2.725 Kelvin, just a couple degrees above absolute zero. This glow is a nearly perfect thermal signal, meaning it has a smooth spread of wavelengths like light from a warm object, and its peak sits roughly at a millimeter in wavelength, the kind of radio wave light radio telescopes can pick up. Think of it as the distant heat left over after a very, very big cosmic bonfire has cooled down, still measurable, but not something you'd roast marshmallows over. As space keeps stretching, every photon of that glow is stretched along with it, which lowers its energy and shifts it to longer and longer wavelengths. In everyday terms, it's as if the notes from a flute were stretched into a bassoon and then into a rumble no human ear can hear. The effect is twofold: photons become less energetic, and they become more spread out, so the overall brightness drops dramatically. A practical example is a perfume bottle in a room. Open it in a small room and the scent is strong, but then take it into a huge cathedral and the smell thins out until you can't detect it. Eventually the microwave glow will be so redshifted and faint that even the best detectors would struggle to separate it from other background noise. Radio telescopes that now see the CMB's smooth glow would instead pick up a soup of longer wavelength interference and local radio chatter, much like trying to listen to a distant station as it slips below the static. For a future astronomer, the sky would lose that clean, even whisper that tells of an early hot phase, and reconstructing the universe's origins would be far harder, like trying to infer a concert from a single parking lot echo. Right now, the fact that the glow is visible at microwave wavelengths is what lets scientists map tiny ripples in it and learn about how matter arranged itself. Instruments tuned to microwaves act like very sensitive microphones, catching the faintest cosmic notes. Later, when those notes have stretched into inaudible bass, the cosmos will look quieter and emptier from an observational point of view. Funny to think about, but future cosmologists might need to invent a brand new set of detective tools, or else accept that some evidence simply drifts away with the expansion. The fate of matter, dust, atoms, and quarks. Even the tiny speck of dust on your bookshelf is built from the same basic ingredients as planets and stars, atoms, which in turn are made of even smaller pieces. Atoms have a central nucleus peppered with protons and neutrons, and a cloud of electrons around that nucleus. Protons and neutrons are themselves made of quarks, tiny bits that never appear alone under normal conditions. Think of atoms as a house made of bricks, protons and neutrons as sturdy bricks, and quarks as the little pegs inside those bricks that hold everything together. Atoms are mostly empty space, which is an odd fact that helps explain how the final unraveling could proceed. If protons are unstable, a possibility in some theories, then the bricks of matter would slowly break down into lighter particles and radiation. Nobody has watched a proton fall apart yet, so this is a live question in physics rather than a confirmed fate. In practical terms, if it happens, ordinary things like dust, rocks, and even the remains of long-dead stars would gradually turn into a diffuse glow of lighter particles, like sugar dissolving invisibly in a vast cosmic cup of tea. If protons do not decay, a different picture emerges where matter survives longer but becomes ever more lonely. Stars will go dark, galaxies will drift apart, and most atoms will be stranded, no longer able to form new structures. Black holes will swallow what they can and then slowly leak away their mass through a process predicted by combining quantum ideas with gravity. That leakage, called Hawking radiation, turns the black hole's mass back into particles and light. Picture a balloon with microscopic holes. it loses air so slowly you barely notice, until one day it is empty. Quarks add a special twist to the story. Under ordinary conditions they are tightly bound inside protons and neutrons, never seen by themselves. In particle accelerators on Earth, scientists can briefly free quarks by smashing nuclei at enormous energies, creating a hot, dense soup where quarks move more freely. This quark-gluon plasma is evidence that quarks can be liberated, but doing that on a cosmic scale requires either extreme local energy or a dramatic global event. In one speculative endgame, the universe's expansion could become so violent that it literally tears apart atomic and nuclear bonds, and quarks might be set loose for a short while before everything cools down into unbound particles. Which outcome actually plays out depends on details we don't yet know about, such as whether protons decay and how the mysterious dark energy behaves. The common end pictures share a few practical features. Dusty leftovers will not remain as tidy specks forever, atoms may either decay or be isolated indefinitely, and quarks will either stay locked inside composite particles or flutter briefly in exotic states. A little cosmic irony remains. The same tiny pieces that make up the crumbs under your couch will have the last acts in these far-off futures, quietly finishing as diffuse particles or faint radiation, a rather low-key finale for such persistent characters. Time scales that make billions look tiny. 1 billion seconds is roughly 31.5 years, which already collapses a gigantic-sounding number into something you can relate to. Picture 3 decades, college, careers, maybe even a midlife crisis. A single billion heartbeats, for a person whose heart averages 70 beats per minute, adds up to about 27 years, so your ticker can easily rack up a billion without much fuss. That comparison helps. Billions can be earned by the body in a human lifetime, while the word still feels enormous. Flip the unit and the picture warps again. 1 billion minutes stretches to around 1900 years, long enough for languages to change and cities to rise and fall. 1 billion hours covers a span roughly 114,000 years, a stretch in which entire ice sheets can advance and retreat. 1 billion days equals roughly 2.7 million years, a timescale where continents drift and species evolve. Short human projects, building a city, writing a book, are a blink next to these amounts, and that contrast makes a billion sometimes seem almost modest. Shrinking time, rather than expanding it, reveals the same trick. A billionth of a second is a nanosecond, and light travels only about 30 centimeters, roughly a foot, in that interval. That's why fiber optic signals and computer signals move in measures of nanoseconds. Processors count billions of these tiny ticks every second. Chemical reactions inside your body or a camera's shutter decide their fate in millionths or billionths of a second, so what seems instant to our senses actually contains whole worlds of activity. Putting the pieces together shows why billions can be both huge and tiny, depending on the yardstick. For everyday life, a billion is colossal. For geological or electronic processes, it's mundane. And for cosmic rhythms, it can be a mere punctuation mark. Humor helps. A billion may sound like something that requires a superhero, but sometimes it's just the number of coffee beans a busy cafe grinds in a few weeks. Life in the dimming cosmos, could anything persist? The ultimate constraint on any living system is how much usable energy is nearby. Stars are the usual energy sources for life as we know it, but when starlight fades and the background glow of the universe weakens, organisms would have to find other ways to get work done, grow, move, copy themselves. Small stars that burn slowly hold out longer than massive ones, so pockets of starlight could persist where a dim, steady source still supplies a trickle of photons. Even a weak light can be enough if an organism slows its pace and lives on a microscopic budget. Some real-world life shows remarkable tricks for extreme thrift. Deep beneath Earth's surface, microbes eke out an existence on tiny chemical gradients, eating hydrogen and minerals instead of sunlight. Creatures at volcanic vents live off chemicals coming out of the rock rather than sunbeams. Tardigrades and certain seeds can enter suspended states where metabolism nearly stops, effectively pausing life until conditions improve. These examples tell us that life can survive on scarce, slow energy and can hibernate through long lean stretches. Human technology gives a practical example too: radioisotope generators, which turn slow radioactive decay into electrical power, keep spacecraft instruments alive long after solar panels would fail. Where could such low-key life find fuel in a dim universe? Radioactive decay inside rocks can provide localized warmth and chemical gradients for a very long time, so subsurface niches on rogue planets or cold moons might be viable refuges. Leftover heat from compact objects, white dwarfs and neutron stars, though extremely cold by everyday standards, still carry stored thermal energy that could be tapped. Even theoretical sources like tiny amounts of radiation from evaporating black holes would, in principle, offer a tiny but steady trickle of energy. This is a speculative idea but grounded in the physics that predict such emissions. Life could cluster near any place that preserves a temperature or chemical difference long enough to do work, much like a moth clustering around a single street lamp in an endless night. There are hard limits though, and they're less poetic. Life needs free energy, differences it can exploit. As the universe approaches uniform coldness, those differences fade. Computing, thinking, and repairing bodies all require energy and produce waste heat, which must be expelled into a cooler environment to keep going. If everything is the same temperature, nothing useful can be done. There's also uncertainty about whether the basic building blocks of atoms will survive forever. Some theories suggest they might eventually break down, which would erase familiar chemistry, but that fate is not settled science. If ordinary matter remains intact, long-lived cold heaters and buried chemical stores could host life for astronomical stretches. If not, only more exotic, information-based strategies might remain. A plausible picture is that anything surviving would be tiny, slow, and local. Metabolism stretched out over long periods, organisms that wake up only occasionally to feed and reproduce, and life forms based on patterns of information running on ultra-low-power hardware are all reasonable options. Picture a microbial world that takes 100-year snack to divide once, or a computation that pings a few times a millennium, slow-motion biology and engineering that would seem frozen to us but perfectly busy on their own timescale. It's less Hollywood apocalypse and more extreme frugality, life not exploding into new niches, but finding ways to keep the lights on, figuratively and sometimes literally, in the faintest of rooms. Artificial hibernation and cosmic survival fantasies. Doctors already use controlled cooling of the body to protect the brain after serious injuries, and that simple fact grounds many of the ideas about putting humans into slow, survival-friendly states. In hospitals, lowering body temperature by a few degrees can reduce swelling and give tissues a better chance to recover. It is not magic, just slowing the chemistry so damage happens more slowly. Nature gives clear models. Small mammals and some birds enter torpor to survive food shortages, and bears sleep through winter with their heart rates and activity levels dropped. These real examples show that reducing metabolism is possible, but doing it for long stretches and for humans brings extra challenges. In nature, some animals shrink their daily needs to a whisper and wake up the same animal they were before. Hummingbirds take short, nightly torpor to save energy, and ground squirrels may spend months in a deeply slowed state. People can picture this with everyday things, putting a phone into low-power mode to make the battery last, or sealing leftovers in the fridge to keep them from spoiling. But human bodies are more like delicate electronics. Long dormancy causes muscle loss, bone thinning, and immune weakening if not managed. That means a practical human hibernation program would need ways to keep muscles toned and bones loaded, even while the overall metabolism is down. For space travel fantasies, those big plans to drift between stars while astronauts nap, the attractions are obvious. Less food, less waste production, and fewer psychological stresses from long isolation are persuasive on paper. Actual implementation would require solutions for radiation exposure, because cosmic rays keep streaming even when you sleep. Simple tricks from everyday life offer good metaphors. Just as hikers use compact freeze-dried meals and periodic stretching to stay functional on long trips, long-term hibernation would need staged nutrition, exercise routines built into the pod, and frequent health checks. The phrase, hibernation sleep, sounds cozy, but there would be no snack breaks or commercial breaks in the middle of a centuries-long commute. Research in labs has shown that metabolic rates can be nudged down in small animals and that certain drugs or low oxygen levels change how fast cells work, but translating that to safe, reversible human states is a massive engineering and medical project. Problems include clearing metabolic waste, preventing clots, and keeping the brain's wiring intact so memories and personality survive. Think of thawing frozen food badly and finding the texture ruined. Similarly, careless reactivation of a hibernated human could leave organs malfunctioning or the mind foggy. That's why current medical use of cooling is careful, short-term, and closely monitored. Cryonics, the idea of freezing people after death in the hope of future revival, belongs to a different category. It is a speculative gamble rather than a proven medical method. People who choose it are betting on future technology. That is a personal choice and not the same as medical hibernation used to buy time during emergencies. If a science fiction plot wants to keep characters intact for eons, authors and engineers must also reckon with social and ethical questions. Who decides to revive someone, and under what conditions? These are practical issues that hug the technical ones, and they deserve thought long before anyone steps into an off switch. To cope with the many technical hurdles, designers imagine layered systems, controlled temperature, artificial gravity or muscle stimulation, filtered air, and automated medical checks. Engineers also look at redundancy, multiple backups for life support, because a single failure in a hibernation pod could be catastrophic. A home example helps. A well-designed emergency kit for a storm includes not only water and batteries, but a plan for what to do if the power fails. In the same way, hibernation systems need plans for waking early, dealing with illness, and handling long-term maintenance. There is hope and humor in these plans, too. After all, if future hibernation pods include a gentle chime and a polite, "welcome back" message, that counts for something when you step out after a very long nap. Information and the final ledger of the universe. Quantum theory says that information cannot be destroyed. The mathematical rules that govern the smallest scales keep a record of what happened, even if that record becomes wildly scrambled. In plain terms, if you knew every detail about a closed system right now, the underlying rules allow you, at least in principle, to rewind and recover its past. A shuffled deck still contains the same cards in some order. The order is conserved even if your cat walked across the table afterwards. This idea sits at the heart of why physicists worry about whether the universe ever truly loses information. Some corners of physics make that worry more urgent. Black holes, for example, act like cosmic trash compactors at first glance. Things fall in and disappear from sight. Yet theoretical work shows that a black hole's capacity to store information is tied to the area of its surface, not the volume inside, meaning the edge matters more than the interior. Think of a suitcase that, bizarrely, can only write a summary of its contents on the lid. The summary grows with lid size, not roominess. Because small objects can evaporate away via faint radiation, the question becomes whether the detailed information about what fell in is somehow imprinted on that radiation or smeared out on the surface of the hole, and whether an external observer could ever read it. When people talk about a final ledger of the universe, they mean some ultimate bookkeeping of every bit of information that ever existed, however hidden. In everyday terms, it's like asking, after a party, where is the record of everything that happened, the conversations, the spilled drinks, the broken vase? In physics, the candidates for that record include tiny correlations between distant particles, very low-energy background radiation, or information encoded on cosmic boundaries in a way we do not yet fully understand. Burn a book and the words seem gone, but the ink's chemical energy, the smoke, and the heat carry traces of what was there. Reconstructing the original text would be fiendishly hard but not always forbidden by the laws of physics. Practical limits change the problem from, is it possible, to, is it useful? Even if information survives in scrambled correlations, cosmic expansion, inevitable noise, and quantum decoherence can scatter pieces so thoroughly that reconstruction is effectively impossible. Imagine spilling a box of tiny beads in a crowded city. Every bead still exists, but collecting them all would bankrupt you. The final ledger might therefore be a theoretically complete list that no one could read, a cosmic bookkeeping ledger with no accountants left to balance it. That gap between theoretical conservation and practical recoverability is where much of the modern debate lies, and it has consequences for how we think about entropy, memory, and whether the universe keeps receipts for everything it ever did. Speculative escapes, wormholes and pocket universes. Physicists working with Einstein's theory of gravity found mathematical solutions that look like tunnels connecting far apart places in space, and those solutions are what people call wormholes. They are best thought of as shortcuts through the fabric of space. In plain terms, a wormhole is like a tunnel cut through a mountain so you don't have to drive around it, except the mountain is space and the tunnel bends distance itself. These ideas come from equations rather than observations. They are allowed by the math, but the math also makes clear that keeping such a tunnel open for a traveler is not simple. Ordinary matter, the stuff chairs and people are made of, would pinch the tunnel closed, so physicists say you would need negative energy or exotic matter to hold one open, a kind of energy that behaves opposite to the energy you're used to. Small amounts of negative energy have been seen in the lab in special quantum setups, like the Casimir effect where two metal plates in a vacuum are pulled together by strange quantum forces, but scaling that up to support a human-sized passage is far beyond current technology. Bubble-like pocket universes are a different sort of escape hatch from the cosmos. The idea is that parts of space might inflate and separate, forming their own regions with their own conditions, much like bubbles forming in a pot of boiling soap. Each bubble could have its own rules, meaning the strengths of forces and the types of particles might differ, so chemistry and life could look very different or be impossible there. Think of a block of apartments. Every flat shares the same building, but each tenant decorates differently. A pocket universe might be a flat with a completely different set of furniture and plumbing. Cosmologists use this pocket universe picture to explain why our region has the particular mix of forces and particles that allow stars, planets, and life. Some people point to it when wondering why the universe seems tuned for life, but it remains a theoretical idea without direct proof. Practical roadblocks are huge. If you imagine trying to build a tunnel through a city, you already know about permits, digging, and collapsing soil. The cosmic version would add the problem that the very fabric of space resists being reshaped without strange forms of energy. Observationally, scientists have looked for hints, subtle distortions in how light bends or odd patterns in the background glow of the universe, that might betray a wormhole or a nearby bubble, and so far nothing conclusive has appeared. The quantum effects that hint at negative energy are real and measurable in tiny setups, but they are local and fleeting. Using them to hold open a stable passage is like trying to hold open a cave with a thimble. So while the math permits many exciting possibilities, the bridge from equations to engineering is enormous. The speculative uses people enjoy picturing range from practical to comic. A traversable wormhole could be a freeway to the other side of the galaxy without the long commute, if it existed, although it might come with rules about traffic and tolls no one has thought of yet. A pocket universe could be an escape pod with different chemistry, so don't expect your toothbrush to work the same way there. Humor aside, different physical laws could mean no atoms, or no stable stars, so most pockets would be inhospitable. There are also logical puzzles. Certain wormhole setups allow loops that look suspiciously like time travel, which brings up paradoxes about cause and effect, and physicists take those possibilities seriously because consistency is important to making sense of the world. These ideas stretch both imagination and the known limits of physics. Laboratory hints of weird quantum behavior show that nature can surprise us, and theoretical models give a language for thinking about tunnels and bubbles. Still, no clear observational evidence supports the existence of usable wormholes or neighboring pocket universes, and making one, or finding one, remains a topic for careful study rather than moving advice. Curiosity about these possibilities sparks creative experiments and thought, and if nothing else, they provide a fun cosmic mental exercise, a useful reminder that the universe might be stranger than we usually encounter in daily life, even if we won't be booking an interbubble vacation anytime soon. Thermodynamic pessimism versus hopeful engineering. Physical laws tell us that in a closed system, the amount of energy you can actually use to do work tends to fall as things spread out and become more uniform. That spreading is what scientists often call entropy, which you can think of as how mixed up or unavailable energy has become. a hot cup of coffee cooling on the table is a small, everyday example of the same basic effect. Batteries lose their charge, ice melts, and a steaming pot on the stove eventually cools down, all show usable energy becoming less available for doing useful tasks. Engineers and physicists use these facts to explain why, on the largest scales, processes tend toward states where there are fewer differences to exploit for work. Many people take that steady march toward uniformity as the pessimistic view. When there are no temperature differences, no pressure differences, nothing for engines to push against, machines and life itself can't extract useful work. A refrigerator stops being a refrigerator if the kitchen is as cold as the inside, just as a car can't run if its fuel and the environment are in the same low-energy state. Everyday examples make this intuitive. You can't get heat out of a room by putting a cold spoon into it, and the same logic scales up. It's a blunt fact, and not a cheery one. Think of it as nature slowly flattening the hills of opportunity into a featureless plain. Practical engineering, though, looks for ways to keep the hills for as long as possible or to build machines that can do useful things with the shallow slopes that remain. Waste heat recovery in power plants and factories is a concrete example. Instead of dumping hot exhaust into the air, engineers route that warmth to heat buildings or preheat incoming fluids, squeezing extra usefulness from energy already spent. Regenerative braking in hybrid and electric cars captures kinetic energy when slowing down and returns it to the battery. Heat recovery ventilators in modern homes swap heat between incoming and outgoing air to reduce heating bills. There are also active research paths like very low energy or reversible computing, which aims to perform some calculations with much less energy loss by avoiding needless bit erasure, like doing bookkeeping without throwing away receipts. None of these tricks violates the basic rules. There are hard efficiency limits tied to how big the temperature or energy differences are, and you can't magically create work from perfect sameness. The key is extending useful gradients and using them cleverly. Harvesting sunlight is simply taking advantage of a large, ongoing flow of high-quality energy rather than waiting for what remains in a closed box. In practice that means smarter insulation, better recycling of materials and energy, localized computing near energy sources to avoid transmission losses, and designing devices that can be easily repaired so their internal order isn't trashed and thrown away. Pessimism reminds engineers of the ceiling. Hope is the toolbox that keeps us building under it, and sometimes the tools look like common sense dressed in clever physics, which, happily, can be a lot of fun to invent. Simulating the end, virtual final seconds. Scientists build virtual universes on computers to test how different endings could play out, running many scenarios and comparing them to what telescopes actually see. Some scenarios are simple ideas. One ends in a slow fade where everything evens out and motion stops, another rips space apart with a growing pull, and another collapses back in on itself. These are described in plain terms so anyone can follow. To simulate this, models include gravity, the pull that keeps planets in orbit, energy flows, and a mysterious component called dark energy, which acts like an invisible push that can speed the universe's expansion. The codes treat these ingredients as rules that evolve over time. Think of it like a very fancy weather forecast for the cosmos. You feed in current observations, choose physical rules, and let the computer, weather, run forward to see how things settle or spiral away. The nuts and bolts involve huge numbers of particles representing stars, gas, and dark matter, plus rules for how they interact. Higher detail means more particles and more computing work, similar to how a high-resolution camera captures more pixels. Lower detail runs faster but loses small features. Researchers use established simulation engines such as Gadget or public projects like Illustrious TNG to handle the heavy lifting, while supercomputers and graphics processors do the fast arithmetic. For everyday comparison, it's like using a flight simulator to train a pilot. The better the simulator, the more realistic the maneuvers look, but you still can't exactly recreate turbulence in every gust. Visualization turns raw data into things people can actually see and feel. Scientists often compress billions of years into seconds or minutes so patterns become visible, using time-scaling tricks that preserve relationships while letting viewers perceive long-term trends. Some groups convert simulation outputs into immersive VR experiences or detailed planetarium shows with real-time flithroughs, and game engines like Unity or Unreal are sometimes used to render scenes with convincing light and texture. An analogy from daily life: just as a GPS condenses a long road trip into a few screen images and turn-by-turn directions, visualizations condense cosmic timelines into understandable slices. And yes, it's a bit like watching a very slow movie where the hero never quite learns to spell. Simulations also test what we would actually observe from Earth if a particular ending were true, looking for specific signatures such as shifts in galaxy distribution or the timing of cosmic background changes. This is practical science, not sci-fi. Models that don't match telescope data get revised, much like a recipe tweaked after a cake comes out too dense. There are limits. Unknown physics or missing ingredients can send a model off course, and resolution limits mean tiny effects may be smoothed over. Still, these virtual experiments let researchers narrow down possibilities and suggest what to look for next with real instruments. The human side matters too, because visual, interactive simulations help scientists and the public think differently about abstract outcomes. They uncover surprises, prompt new questions, and occasionally produce images so striking that they spark outreach and inspire students. And for those worried about doom and gloom, remember that these are controlled tests run on silicon and code. No actual universe gets harmed in the making of the simulation, though your coffee might grow cold while you watch. Observational clues from our cosmological measurements. Measurements of distant starlight show that most galaxies are drifting away from us, and the farther a galaxy sits, the faster it seems to recede. This stretching of light makes it appear redder, a bit like the change in pitch you hear when an ambulance passes by, and that simple observation is one of the basic pieces of evidence about how the universe is growing. Astronomers use that red tint to map the speed and distance of galaxies, and by comparing many of those measurements they build a picture of cosmic expansion that's surprisingly reliable, even if the universe itself is a stubbornly private client. A faint glow fills the sky in radio and microwave light, and it acts like a cosmic after-dinner coffee stain, the leftover heat from an early hot phase that now sits just a few degrees above absolute zero. That glow is almost perfectly even, but tiny temperature wiggles are embedded within it, and those wiggles are crucial. They are the fingerprints of small density variations that later became stars and galaxies. Think freckles on a fruit that tell a farmer where to pluck. Sensitive satellites and telescopes have mapped those patterns in great detail, giving us a neat list of what kinds of stuff must be in the universe and how clumpy it was at the start. Explosions of certain stars act as reliable distance markers because they reach nearly the same peak brightness, serving like identical light bulbs placed at unknown distances. By measuring how dim they look, astronomers deduce how far away they are. Observations of these stellar beacons revealed a surprise: the universe's expansion is not slowing down, it's speeding up. To account for that acceleration, scientists infer the presence of a mysterious component that pushes space apart. When all clues are added up, the afterglow wiggles, the galaxy clustering patterns, and the bending of light by mass, the best description is that ordinary atoms are only a small part of the budget. Dark matter contributes much more, and an even larger share acts like a repulsive energy. Roughly speaking, ordinary matter makes up about 5 of the total, dark matter about a quarter, and the rest behaves like that repulsive stuff. Different measurement methods sometimes disagree in subtle ways, which keeps the field lively and humble. Local measures of how fast space is expanding can give slightly different answers than the values inferred from the early universe glow, and that tension might be a sign we're missing a piece of the puzzle, or that calibration routines need polishing, like when two cooks can't agree on a recipe but both insist it will feed the family. Gravitational lensing, where mass bends light and acts like a warped glass cup, provides an independent check by mapping mass directly, and large galaxy surveys trace the cosmic web that results from gravity pulling matter into filaments and clusters. Ongoing and upcoming measurements aim to sharpen these clues, reducing uncertainties the way better scales help a baker improve a cake, and they continue to shape which cosmic endings remain plausible while ruling out the wilder ideas. Philosophical ponderings, meaning at the end. Many thinkers notice that the question of meaning changes when the endpoint of everything is put on the table. if everything will end, some ask whether anything truly mattered in the first place. Philosophers typically divide responses into a few clear stances. Some hold that meaning comes from outside us, a purpose built into the world or given by a tradition, while others argue that meaning is something people make for themselves, like a painting or a recipe. To keep things simple, think of one view as meaning discovered and another as meaning created. Both approaches have practical consequences for how someone lives day to day. One practical consequence is that people often ground meaning in relationships and projects because those persist long enough to feel substantial. Parents, for example, invest in a child not because they expect cosmic endorsement but because the relationship matters now and will ripple into the near future. Leaving a garden for next season is a small-scale analogy. Artists make work knowing the world will change. That act of making can feel meaningful regardless of ultimate outcomes. And scientists keep records and share knowledge for the benefit of others, which is a very literal way of saying, first care about tomorrow even if first won't be here to see it. A different reaction comes from those who say meaning collapses if the cosmos ends. This is often labeled nihilism, which simply means no inherent meaning. Some people find that thought bleak, while others find it oddly liberating. If nothing is prescribed, then you can write your own rules. That freedom doesn't automatically make life easy, though. Responsibility and often awkward choices follow. Volunteering at a shelter, starting a small community choir, or fixing an old bike can become concrete ways to build meaning under that open sky. Another approach mixes ritual and curiosity. Small rituals, birthdays, yearly reunions, even a simple habit of telling someone you love them, create a sense of continuity that softens the thought of an ending. Curiosity, too, matters. Pursuing knowledge or beauty doesn't require a cosmic warranty to feel important. Practical tips include keeping a journal to track values over time, committing to a project that benefits others, or simply scheduling regular conversations about what matters with friends. Humor helps, and sometimes saying that you're saving a seat for the future when you plant a tree feels just as meaningful as any grand metaphysical claim. Pop culture visions of cosmic apocalypse. Movies, TV shows, and comics love to turn the end of everything into a dramatic set piece, and they do it in a handful of familiar ways. Asteroids and comets smashing into a planet get shown as giant explosions that level cities, think Armageddon or Deep Impact, while rogue planets on collision courses become slow, inevitable dread in films like Melancholia. Black holes and strange physics show up too. Interstellar uses a massive, spinning black hole as both a plot engine and a visual wonder. Writers also riff on more exotic ideas, such as the universe tunneling into a new state. Scientists call that vacuum decay, but storytellers explain it as a bubble of reality growing and popping everything it touches, like a soap bubble swallowing a room. Humor crops up in unexpected places. Douglas Adams' The Hitchhiker's Guide to the Galaxy casually demolishes Earth for a bureaucratic reason, and that deadpan absurdity keeps cosmic doom from becoming too grim. Many pop culture works focus less on the mechanics and more on how people behave when doom lurks. Satire is common. Don't Look Up uses a comet to show denial, media spin, and political gridlock, while other stories portray military scrambling, scientists arguing, and ordinary folks trying to get home or make coffee. Everyday comparisons help these moments land. An evacuation scene can feel like a chaotic airport on a holiday, and that helps viewers relate. At the same time, some creators deliberately slow things down to explore emotion. A family dinner while the sky goes strange can be quieter and more affecting than an all-out explosion. Comic books and superhero sagas raise the stakes even further, with crossover events in Marvel and DC where entire realities tremble, forcing alliances and betrayals on a cosmic scale. Visuals and sound design do heavy lifting in shaping how audiences experience apocalypse. Practical effects, sweeping CGI, and a quiet soundtrack can make a small object look terrifying or a large catastrophe feel eerily intimate. Interstellar's depiction of a black hole emphasizes scale and silence, while Melancholia's slow, lyrical shots turn planetary collision into a meditation. Filmmakers will often use ordinary items to sell the enormity, a child's toy floating in a ruined living room, or a kettle still boiling on an abandoned stove. That contrast, small domestic details against cosmic collapse, keep stories grounded and relatable. Comic panels and TV serials use bright colors, sudden cuts, and cliffhangers to sustain tension across issues or episodes. Popular depictions also influence how people think about real-world risks and solutions. The idea of deflecting an incoming rock with a spacecraft went from science fiction trope to actual policy discussion, and there have been real test missions to see how an asteroid might be nudged off course. Space agencies tracking near-Earth objects appear in news and fiction alike, which helps the public grasp that some threats are monitored and sometimes mitigated. Stories can prompt practical conversations without getting bogged down in technicalities. A film that shows experts collaborating may inspire support for funding planetary defense, while a satire about denial can nudge viewers towards civic awareness. In other words, pop culture makes big, distant dangers feel like something we can talk, and sometimes laugh, about, even while the soundtrack swells behind the final cut. What a photon sees, the last journey of light. A photon moves at the cosmic speed limit, 299,792 kilometers per second, and it carries energy that shows up as color, heat, or radio signals. It has no rest mass, which is why it never slows down, and that simple fact already sets the rules for everything that follows in its voyage. Picture a single particle of light leaving a light bulb or a distant star. Its fate depends on what it meets and the space it must cross. As space itself stretches, the photon's wavelength stretches too. That means blue light can slowly become redder, and high-energy light can become low-energy light, just by virtue of the room getting bigger. Everyday life gives a useful analogy. Put a rubber band around a drawing and pull it, the picture becomes longer and the colors smear. The photon's wavelength does something like that when the universe expands. Sunlight turning orange at sunset is a nearby, familiar example of the same basic idea, because short blue wavelengths are scattered out and the longer red ones keep going to your eyes. Collisions with matter change a photon's path or end its journey altogether. In the atmosphere, tiny particles scatter blue light in all directions, making the sky blue. Larger dust grains scatter reds and oranges, which is why dusty sunsets look extra dramatic. Sometimes photons bounce around inside a cloud or a piece of glass many times before finally escaping, similar to how a pinball ricochets until it drops into the hole. Other times a photon is absorbed and its energy is taken up by an atom or molecule, warming it, knocking an electron into a higher state, or starting a chemical reaction, the process behind photosynthesis and in your microwave oven, where many microwaves are absorbed by water molecules and turned into heat. Gravity can bend a photon's path without touching it. A heavy object warps the space around it, and light follows the curves like a car following a road that has been bent. Astronomers treat that bending as a kind of magnifying glass. A distant galaxy's light can be split into arcs or multiple images by a massive cluster in front of it. For the photon, this is not drama but simple geometry. Travel through a dented sheet and your route changes. In an extreme case, if a photon strays too close to a black hole, it can cross a boundary beyond which escape becomes impossible, and that marks a hard end to its journey. Not every photon gets fancy treatment, many simply coast until they run into something that absorbs them. Some travel across vast empty regions for incredible distances, gradually losing energy and changing wavelength, until detectors or dust grains finally stop them. Others might redshift so much that they become part of a pervasive background of faint microwaves that pervade space, low-energy photons that once had much more pep. The last leg of a photon's trip is often quiet. There is no ticking clock experience for light itself, because the usual idea of time doesn't apply the same way at light speed. Still, for observers and instruments, that final arrival or absorption is the big event, and from it we learn about conditions along the entire route, composition, motion, and the stretching of space. Practical examples help make all this sensible. A beam from a flashlight entering fog gets scattered, making the beam visible from the side but weakening its reach. A radio signal sent across town might pass through buildings, reflect off surfaces, and finally be absorbed by a receiver's antenna. Replace the town with the universe, and the same categories, scattering, absorption, bending, and stretching, govern the photon's fate. A little humor keeps it human. A photon is both the universe's most persistent traveler and the worst at checking luggage. It never loses momentum, only wavelength, and it can be absorbed by the tiniest speck of dust as if that speck were a five-star hotel with irresistible room service. The mathematics behind cosmic demise. Mathematicians turn observations of how the universe stretches and how energy spreads into compact formulas that can be pushed forward in time to see possible endings. These formulas are mostly recipes for change. They tell you how fast something will grow or shrink at any moment, and then you add up those little steps to get a long-term picture. One common kind of recipe is the differential equation, which sounds fancy but is simply a rule that says, if 10th is changing at this rate now, then after a little while it will be this much different. Think of it like a cooking timer that constantly adjusts the heat based on how much the soup is boiling. Simple to state, sometimes fiendish to solve. A second basic ingredient in the math is how fields and forces weaken with distance. Gravity and light spread out as you move away, so their influence drops quickly. A streetlight seems much dimmer when you stand twice as far, and the math captures that dimming cleanly. Scaling laws like this are useful because they let scientists estimate whether distant galaxies will remain bound together or drift apart forever. To make the point with a home example, when you spread butter on toast, the same amount of butter covers more area as you thin it out. In the cosmos, the same fixed amount of stuff gets spread over ever more space, and equations track that dilution. Entropy is another core concept in the calculations, but it can be explained without heavy jargon. Entropy counts how mixed up things are. A tidy sock drawer has low entropy, a laundry basket has high entropy. The mathematics says that, overall, disorder tends to increase, which is why a hot cup of coffee left on the table cools to room temperature and never spontaneously gets hotter. Applying that idea to the entire universe is straightforward in spirit. As energy becomes more evenly spread and less usable, the universe heads toward a state where nothing useful can happen. Picture every battery in your house slowly losing its charge and no one inventing a charger that actually works, mildly depressing, and mathematically tidy. Different end scenarios come from changing a few numbers that plug into those recipes. If the expansion of space accelerates strongly enough, the models will show forces within galaxies and even within atoms eventually getting overwhelmed. The math looks like a runaway exponential, similar to compound interest that keeps doubling faster and faster. If expansion slows and reverses, the equations resemble a slowed ball thrown upward that eventually falls back down, implying a collapse where everything squeezes together. And if energy simply runs out for doing work, the equations predict a slow approach to thermal lifelessness. In each case the same tools, differential rules, conservation relations, and statistical counts, are rearranged to tell different stories. Uncertainty plays a big role because the long-term outcomes depend sensitively on a few measured inputs. Tiny changes in the measured expansion rate or in how a mysterious repulsive component behaves lead to very different futures when those small differences are extrapolated for huge spans of time. This sensitivity is the same kind of mathematical feature that makes weather forecasts unreliable more than a week out, or makes your savings plan look very different if the bank changes the interest rate by a hair. Mathematicians therefore spend a lot of time estimating error ranges and running many simulations with slightly different starters to see which endings are robust and which are fragile. Practical computation blends pen and paper formulas with brute force numerical work. Some equations can be solved exactly, but many cannot, so computers step in and march forward in tiny time steps while tracking dozens of interacting factors. It is similar to following a recipe with 1,000 ingredients. Nobody tastes the whole thing at once, instead you sample frequently and adjust. Scientists also test their models against what telescopes actually see now, because a model that mismatches present observations is like a cake recipe that yields soup, that helps weed out unrealistic mathematical endings. Finally, a pinch of humor keeps things human. The cosmos follows rules that are mathematically elegant, but the conclusion is often a mundane bookkeeping problem of energy and probability. The math doesn't care whether we find the ending exciting or scary, it just sorts possibilities like a cosmic accountant. And unlike your sock drawer, the universe doesn't fold itself back into order. at least according to the same tidy equations, so mathematicians keep refining their tools, measuring inputs more precisely, and occasionally making analogies to toast and laundry to remind everyone that abstract equations have very down-to-earth meanings. Alternate endings, cycles, bounces, and renewals. Some cosmological ideas see the universe as rhythmic rather than terminal. One such picture replaces a single beginning and end storyline with a sequence of expansions and contractions. The cosmos grows, slows, then shrinks, only to bounce back into a new expansion. This bounce picture is sometimes offered as a way to avoid that awkward notion of everything squishing into an infinitely small point. Instead, the universe compresses to a dense state and then rebounds, like a cosmic rubber ball. In plain terms, think of a balloon you squeeze and then let go, only on a scale so huge it makes seasons and centuries seem like blinks. Scientists explore whether this rebound could smooth out the universe's early wrinkles, and whether any faint fingerprints of a previous cycle might still be visible in the sky. Another line of thought treats endings as collisions and renewals. In these ideas, the universe we know might be one of several large objects, call them sheets or membranes, that occasionally bump into each other. When they meet, energy is released and a fresh era of expansion begins. It's a bit like two pancakes slapping together and sending batter flying, only replace batter with space, time, and a lot more math. Researchers look for traces of such dramatic encounters by studying the cosmic microwave background, the faint afterglow of the universe's hot past, and by hunting for subtle ripples called gravitational waves. So far the evidence is subtle and contested, but the search continues, like detectives scouring wallpaper for clues of a previous room layout. A gentler renewal idea imagines the cosmos fading into a very smooth, empty state that can be practically rescaled into a new beginning. Under this scenario, the universe stretches so much that structures dissolve, leaving behind mostly radiation and very low-energy remnants. Once that peaceful sea is reached, it can be reinterpreted as the seed of a new hot phase. Picture an old photograph that's been smoothed and lightened so thoroughly that it could be copied again as a fresh snapshot. This approach sidesteps a violent crunch and instead uses a kind of cosmic ironing out to set the stage for renewal. The technicalities can be subtle, but the basic image is simple, ending by erasing complexity and beginning by starting over from a very clean slate. Practical questions quickly come to the fore: can disorder be reset, and what role does the universe's accelerating expansion play? Disorder, often described with the word entropy, tends to increase, like a bedroom that gets messy unless someone tidies it. Any cyclic or bouncing model must explain how entropy doesn't accumulate forever, or how the universe finds a way to restore low disorder for the next cycle. Observations of the universe's accelerated expansion, driven by a mysterious dark energy, also complicate cycles. If expansion keeps speeding up, bringing the cosmos ever farther apart, triggering a future contraction becomes harder. Astronomers therefore test these ideas by comparing precise maps of the cosmic microwave background, surveys of galaxy distributions, and searches for faint gravitational waves. No decisive verdict has been reached. The possibilities remain part of active research, and some scenarios fit the data better than others. In everyday life, these cosmic alternatives echo familiar rhythms: breathing in and out, the seasons returning, a clock's pendulum swinging. Humor helps too. If the universe does cycle, it may be that the cosmos is the ultimate optimist, constantly hitting restart when things get awkward. Whatever the true ending, if there is one, the ideas of cycles, bounces, and renewals give a hopeful lens. Endings might be transitions, and renewals might be built into the very fabric of reality, like nature's habit of making new leaves after old ones fall. Could new physics rewrite the finale? Astronomers see the universe racing outward faster than expected, and that tells us the simple picture of how things end might be unfinished. One straightforward idea is that empty space carries a steady push that never changes, like a thermostat set to a fixed temperature. Another idea is that the push slowly changes over time, more like a thermostat someone keeps fiddling with. If that push, what physicists call dark energy in plain terms, turns out to evolve, then the long-term story of the cosmos changes in predictable ways, and we can look for those changes by measuring how fast galaxies move apart and by studying the light from distant exploding stars and the ripples left over from the Big Bang. A more dramatic rewrite comes from the odd behavior of the vacuum itself. The vacuum isn't nothing, it has an energy landscape that might sit in a valley that is only a little lower than a deeper valley nearby. Occasionally, quantum physics allows a tiny patch to jump into the deeper valley and start a growing bubble that spreads at nearly the speed of light. Think of superheated water in a microwave that suddenly boils all at once. The suddenness is what counts. If such a bubble were to form, it would change the rules of chemistry and forces inside it, and anything it touched would be ripped apart, not the kind of pop you want at a party. Lab experiments and particle colliders help us test whether our vacuum is stable by studying the properties of particles that influence that energy landscape. Another route to rewriting the finale is that gravity might not behave exactly as Einstein predicted on the largest scales. Small tweaks to how gravity works, or the existence of extra hidden dimensions, could make the cosmic expansion slow down or speed up in unexpected ways. Picture a trampoline that sags differently when many people stand on it. Change the fabric and the sag changes. Astronomers test these ideas by mapping how galaxies cluster, by watching how massive objects bend light, and by listening for gravitational waves that carry information about gravity under extreme conditions. Practical consequences are easy to describe without getting technical. If the cosmic push grows stronger, bound structures, galaxies, solar systems, even atoms, could be pulled apart in a scenario sometimes called a big rip. If the push weakens, cosmic expansion could slow and gravity might eventually pull matter back together, or else the universe drifts into quiet cold with stars slowly burning out. If the vacuum flips suddenly, life would end quite abruptly and without warning. Current and upcoming observational projects, wide-field sky surveys, precise maps of galaxies, and particle physics experiments, are aimed at narrowing these possibilities so we can stop guessing and start knowing. New physics could therefore change the ending from a slow fade to a sudden rewrite, or to something stranger still. That possibility makes the search exciting and a little unnerving, like opening a mystery novel near the last chapter. Either way, the tools we have now are good enough to rule out many silly ideas, and better tools arriving will keep trimming the list of likely finales. Popcorn remains optional. The role of dark energy in the closing act. Observations show that roughly 2/3 of the universe's energy sits in a mysterious form that pushes space itself outward, and that push is what controls how the cosmos slows down or speeds up. Scientists call this dark energy, a name that highlights how little we understand it. In plain terms, it's like a hidden pressure in empty space that makes galaxies move away from each other faster over time. Evidence for this comes from several independent lines: measurements of exploding stars used as distance markers, patterns in the leftover glow from the early universe, and the way large groups of galaxies cluster. Short sentence. Because dark energy dominates the total energy budget, it effectively writes the last acts of cosmic history, deciding whether the universe ends in a slow chill or a more dramatic unraveling. If dark energy behaves like a constant push, what physicists often call a cosmological constant, space will keep stretching faster and faster on average, leaving isolated islands of bound objects while everything beyond a shrinking horizon drifts out of causal contact. That's somewhat like sitting in a small harbor as the ocean rises and swallows all the roads. Your town still exists locally, but you can no longer send a car to visit your neighbor. Small joke, not the kind of neighborhood where you borrow sugar. Measurements suggest the behavior of dark energy is very close to a simple number often written as W equals 1, which means its pressure and energy density have a particular balanced relationship. This clue favors the steady, persistent push rather than something wildly changing. If that balance holds, the final seconds of the cosmos are not a frantic tear but a gradual fading. Stars eventually exhaust their fuel, galaxies become faint embers, and background radiation cools toward nothing measurable. Short sentence. Alternatively, if dark energy's strength grows with time, a possibility still on the table, it could become strong enough to pull apart galaxies, then solar systems, and conceivably atoms, a dramatic end sometimes nicknamed the Big Rip. That scenario is more like a blender turned up too high. Practical efforts to pin down dark energy's character involve mapping the distances and motions of many galaxies and stellar explosions to get a clear picture of how expansion changed over time. These are not abstract projects, they are like taking precise snapshots of a slowly unfolding movie, frame by frame, to see whether the villain is steady or escalating. Short sentence. Because we don't yet know the true nature of dark energy, its role in the closing act remains the universe's greatest plot twist, either a long, lonely fade-out where the cosmos cools and darkens, or a more theatrical finale that rips the stage apart. A little cosmic irony, and a reminder that the universe's final curtain will be determined by something we are still trying to understand. A timeline of the final seconds in plain English. If space keeps stretching at the pace we observe now, far-off galaxies will drift away until their light can't reach us, leaving our local group alone in an ever-darkening sky. Light from those galaxies gets stretched to longer, weaker wavelengths, a bit like hearing an ambulance siren drop in pitch as it speeds away, and that means less energy arriving here. Stars in our corner will keep burning until they run out of fuel, and then they die in quiet ways. Some become dim, dense white dwarfs that glow like dying embers, others collapse into neutron stars or vanish behind black holes. Picture a city slowly turning off its lights one by one, not sudden, just steadily quieter. After most stars stop shining, the universe becomes a place of leftovers and slow processes. White dwarfs and neutron stars are like glowing coals that cool over time, and binary systems can fling matter into compact objects in occasional, brief flares, rare fireworks against a mostly dark backdrop. Black holes then become the main actors, swallowing whatever drifts too close and holding onto energy and matter for a very long time. Think of them as cosmic vacuum cleaners with a taste for drama, but their messes also take a long time to settle. Black holes themselves are expected to slowly leak energy through a process physicists call Hawking radiation, which is a theoretical prediction that most scientists accept as likely. In plain terms, black holes can emit tiny particles and gradually lose mass. This is not explosive in the movie sense, it is more like a slowly shrinking candle that eventually flickers out. Once the last of the black holes fade, space is left with a thin soup of low-energy particles and photons, a very spread-out, cold bath where energy differences are gone and nothing can be made to do useful work. That's what people mean when they talk about heat death, not a boiling end, but a state so even that nothing new can happen. Like leaving a hot cup of coffee in a room until it matches the room temperature, the warmth is still there, but you can't use it to power anything. There is another, sudden possibility that physicists take seriously enough to mention. The vacuum of space might be in a delicate state that could flip to a lower energy state, and if that flip happens it would race outward at nearly the speed of light, changing the rules of physics as it goes. That would be abrupt and total. No rescue missions, no heroic last-second maneuvers. It would be like a soap bubble popping and the air inside instantly becoming something else, only far more fundamental. This scenario is speculative but grounded in real equations. It's not fantasy, it's just a different set of outcomes allowed by the math, and it would be over before you could finish a single sentence. If one tries to list the final seconds, in plain terms, the sequence depends on which ending the universe follows. In a slow fade to cold, the last moments are an almost invisible unraveling, the dimmest photons stretch until they are practically undetectable, the rare particle interactions peter out, and the universe becomes an ever more uniform field with no gradients to exploit. In a sudden vacuum flip, the final seconds for any given location are simply the arrival of the transition front, and there is no gradual farewell, one instant of ordinary physics replaced by another of a different kind. If matter is unstable on very long scales, individual atoms might decay into lighter particles and radiation, ending the plausibility of solid structures, that would be gentle at small scales but total in effect. None of these endings resemble cinematic explosions, they're either painfully slow fades or impossibly swift changes, and either way, they'd be bad news for coffee and shoes. Final thoughts. Astronomers watch the sky and see that space itself is getting bigger, and that change tells us a lot about how the cosmos might end. Light from faraway galaxies shows a steady stretching, like colors pulled thin on a rubber sheet. That stretching is a clear signal that things are drifting apart. Current measurements point toward a continued pull outward, which means the ending will likely be slow and quiet rather than a sudden explosion. The takeaway: the universe's final moments are shaped by how space grows, and we can read that story by studying the light around us. One possible ending is a long fade, where stars run out of fuel and everything cools down until there's no useful energy left. Think of a pot of soup left on a stove until it reaches room temperature. It's still there, but it's not doing much. Another idea is a tear-apart scenario, where the stretching gets so extreme that even atoms would be pulled apart, like overstretching chewing gum until it snaps in tiny pieces. A collapsing ending is also discussed, though current science favor expansion. If collapse did happen, it would be more like compressing a sponge back to nothing. These are not just wild guesses. Each comes from how we observe motion, light, and energy in the cosmos today. Beyond the physics, there are practical and human effects to consider. Scientific work aimed at understanding these endings pushes technology forward: better detectors, sharper images of the sky, and new math to handle big problems often find their way into tools used in medicine and computing. Artists and storytellers borrow these ideas too, creating vivid paintings and novels that help people grasp vast timescales in a friendly way. And for everyday life, the cosmic perspective can be oddly useful. It nudges us toward long-term thinking, which is handy when making decisions about climate, infrastructure, or education. So what should we carry away from thinking about those final seconds? Curiosity, for one, keep asking questions and looking up. Kindness, for another, when viewed against the huge backdrop of space, small acts matter to the people around us. Enjoy a good sky watch now and then. No, you don't need to hoard supplies for the universe's last act. There won't be a dramatic curtain call you can plan around, but a little humor and a few more night walks under the stars won't hurt. So, what did we learn in these last, quiet seconds of everything? In short, the universe could fade into an ever-cooling, empty silence. Think of coffee left on the counter until it's lukewarm forever. It might stretch so far that even atoms get pulled apart. Imagine pulling a rubber band until it snaps into nothing, or it could collapse back like a cosmic washing machine cycle, squeezing everything together again. We talked about why these ideas are guesses, because the cosmos is big, weird, and likes to keep secrets, and why none of this changes your breakfast plans today. Your toast is safe. If this felt a little cold and a little awe-inspiring, that's okay. Humans are tiny on a cosmic scale, but our curiosity is huge. You, the person watching right now, are part of the story, asking questions, picturing the end, and laughing a little at the idea that even the universe might someday take a very long nap. If you enjoyed this cosmic thought experiment, stick around, there's more. Next time we'll flip the script and explore how everything began, with simple explanations, real-life examples, and maybe one more bad cosmic joke. If you want more videos like this, like and subscribe, and tell me in the comments which ending you found most believable or most comforting. Share the video with a friend who enjoys big questions, or bad puns. Thanks for staying until the final seconds. Keep wondering, keep joking, and keep your coffee warm while the universe figures itself out.